Model Context Protocol, MCP. At NDepend, we've put our hands in it. We built an open-source C# MCP server based on our product API. Results are beyond our expectations. This video explains what is MCP, what we did, and what we learned. Let's start with a demo. So here we have VSCode with the Note-A-Time solution loaded. Copilot is interacting with the LLM Claude Sonnet. Now let's ask Copilot a simple question. Which methods are less maintainable in this solution? Copilot is thinking. And look at this, it automatically called two tools from our NDepend.MCP.Server, initialize from solution and search code metrics. The result is a list of complex methods. The best part, I can click directly on any of these results to jump straight to the code. An MCP server is essentially a collection of tools. Here's the code for our server in Visual Studio. Our server references the Model Context Protocol NuGet package. This is what allows us to declare each tool as a simple public static C# method. Here's the method for our initialize from solution decorated with the MCP server tool attribute. We've written detailed descriptions for both the tool itself and its parameters. Here's what's happening. We're asking Copilot to provide the solution file path that's currently loaded in Visual Studio or VSCode. This initializes our MCP server with its associated NDepend project. Once that NDepend project is loaded, all the other tools can use it. In the Copilot window, we can actually see the parameters and results for each tool that was called. The second tool called is Search Code Metrics. Notice it has several filter parameters and threshold parameters. The filters weren't initialized because our request simply said, in this solution, pretty generic. But the thresholds, those were automatically set to flag maintainability index values lower than 50, which represents poor values for this metric. In our metric tool MCP description, we provide a whole range of code metrics, things like maintainability index, complexity, and code coverage. We also explain what constitutes bad values for each one. Here's something important. Notice how the metric tool description starts by asking to call the initialize tool first. Actually, all our tools do this. No tool can work without initialization, so we're asking the agent to orchestrate the tool calls properly. Then we also provide a description for each parameter. The tool call then starts with logging enabled. We reuse the session initialized during the first setup call. And we finish by querying the NDepend API to apply filters and thresholds and retrieve code elements and metrics. We've got more demos and code reviews coming, and things are going to build from here. But before we dive deeper, let's take a step back and understand the fundamentals. How does Copilot actually decide which tools to call, and how does it determine which parameters to pass? Let's start with the Large Language Model, LLM, which is excellent at understanding prompts and generating responses. With Retrieval Augmented Generation, RAG, the LLM can retrieve external information from enterprise data or the web to enhance and ground its answers. Then there is an agent that can query the LLM. In MCP terms, the agent is called the host. The agent is aware of one or several MCP servers and knows about each available tool and resource. We'll explain later how Copilot discovers our MCP server. We will also see that our MCP server can perform some actions. The agent uses an MCP client that handles instantiation and communication with each MCP server. The connection between agent and server can use standard I/O. This is what we used in our demo, where the NDepend.MCP server runs locally to access the code currently being edited. Alternatively, the connection can use HTTP with server-sent events when the server is remote, which our MCP server also supports. All messages are formatted using JSON RPC. The MCP protocol is quite rich, supporting tool discovery and allowing servers to send async events back to the client. Now, with this architecture in mind, let's replay our first demo. We asked Copilot which methods are less maintainable. Somehow, Copilot knows about the available tools and their descriptions. The agent compiles the prompt along with the tools list and sends this to the LLM to determine what should happen next. Claude processes this. We could even watch it thinking in VSCode Copilot. The LLM instructs the agent to first call the initialize tool, then call the metric tool with a threshold. This is where the magic happens. The LLM decides the action plan based on the prompt and the available tools. Copilot then calls the appropriate tools and receives back a list of less maintainable methods. Finally, it asks Claude how to best format the result. In our metric tool description, we specified the desired format, single-click navigation and indexed lists, enabling users to say things like improve number 5. And there's the result. Before moving on, let's mention that this MCP explanation was inspired by Tim Berglund's video. Now let's see how to register an MCP server in Copilot using VS Code or Visual Studio. This is done with an MCP JSON configuration file. The file can contain one or more MCP server registrations. Here is an example. One HTTP server using SSE and one local server using standard input and output. The MCP JSON file can be user-level, applying to all solutions, or solution-specific with or without source control. In VS Code, the command palette gives you some MCP commands. You can list installed MCP servers, like our NDepend.server, or add a new one. A server can also be uninstalled directly from this menu. And for the best experience with MCP tools, it's better to be in Copilot agent mode. In Visual Studio, you can list all MCP servers and their tools from the tool icon. Here, you can see the built-in GitHub Copilot MCP server with its tools, as well as the NDepend.MCP.Server. Each tool can be enabled or disabled, and hovering over a tool shows a tooltip with its description. Also, Copilot will first ask for your permission before running any tool. Finally, in the Extensions/MCP Registries menu, you can browse and install MCP servers from the web. In this section, let's see how an MCP server can add value to GitHub Copilot. Let's ask Copilot again, which method is less maintainable, but this time, don't use any NDepend tool. Without MCP, Copilot parses the codebase using regular expressions and sends large portions of code to the LLM. This process takes around 2 minutes and consumes a lot of LLM tokens. Compare that to our MCP metric tool, which gives the same answer in under a second thanks to 2 decades of building fast and accurate .NET code analysis. So let's summarize the MCP tool benefits in this scenario. First, it's objective. The code metrics are computed by NDepend from their definitions. There is no hallucinations from the LLM. Next, it's fast. Tasks that can take minutes is done in a second. It's also cost-effective because it uses far fewer LLM tokens. That means you save money and resources. And finally, it's private. None of your code is ever sent to the LLM. Only the NDepend.MCP.Server sees your code, and it runs entirely on your premises. Of course, these benefits depend on the scenario. Before building an MCP tool, always ask yourself whether it truly adds value compared to the traditional agentic approach. Now, let's see a tool performing an action. We ask Copilot which dependencies exist for the NodeTime namespace. The MCP tool named ListDependency is called. It generates an SVG diagram, opens it in the browser, showing the architecture around NodeTime and the structure of its child types. We can see in the call parameters that Copilot asked for direct callers and callees for the namespace NodeTime. It also set the parameter export to graph to true. The tool also returns in and out dependencies in a paginated result. More on pagination later. Copilot even provides source links for each dependent and lists the .NET framework dependencies. Here is the list dependency tool source code. A single call to the NDepend API with the targeted code element generates the SVG diagram. In this demo, the tool safely generated the SVG graph and opened it, a harmless action. But not all actions should be automated. Would you let an agent or an MCP tool send emails from your inbox as if it were you? NDepend's ruling engine detects issues across your solution. Architecture flaws, code smells, security vulnerabilities, design problems, and more. It can focus on new issues since a baseline, and with some config, it imports Roslyn Analyzer and ReSharper inspection issues too. We built an MCP tool to query these issues via NDepend.API. Here's the plan. List some issues, have Copilot edit code to fix one, then walk through how we guide Copilot at every step. Let's ask Copilot which new code smells in this solution. It initializes the MCP server with the solution. It invokes our MCP tool list all rules summary to understand what code smells means in NDepend terms, and finally, it runs the tool list issues. Result: 3 new code smells added since the baseline. Each shows rule name, description, severity, and tech debt. We've got a type with too many methods, a method with too many overloads, and local time, already at 72 methods, now with 2 more added. Notice the issues spotted are numbered. That's intentional. We instructed Copilot to do this, so users can easily target a specific issue. Let's fix number 3. Copilot calls another tool to get full details, guidelines from the NDepend rule, plus a plain English description of the problem, and for some rules, extra specific info. Remember, the more meaningful the data, the better the fix. Now it strategizes, reading source code and querying Claude's Sonnet LLM, explaining each step as it goes. Solution: Copilot creates a new static class to host those new properties, keeping local time cleaner. It updates all property calls accordingly. Final step: Copilot suggests we keep the changes and build to verify everything compiles. Hold on, we talked about the baseline, but which baseline? Let's get some details by asking. The tool getAnalysisResultInfo is invoked to get the information from the MCP server. So, what happened? First, the MCP server initializes. Then, it calls the tool List All Rules Summary, a required step before listing issues. Why? We asked for code smells, so Copilot needs to know which rule categories match that term. It grabs all available rule categories and asks the LLM which ones match code smells. Next, it calls the tool List Issues. The rule category filter is set to code smells. The filter issues change status is set to new. Finally, get issue detail to fix it is invoked. The issue gets pinpointed by rule ID, source file, and line number. Back comes the rule description, issue explanation, and fix guidelines. Everything Copilot needs to solve it. And that's how you guide Copilot to discover and fix issues. This one was simple, could have been manually fixed, but for complex multi-file issues, the time saved can be substantial. MCP tools for querying issues, diffs, metrics, and dependencies? This is great, but what if you could query or rule anything in your code? That's exactly what this section is about. Let's start with how code querying works in NDepend. In NDepend, code rules are C# link queries over the code model. Click anything in the dashboard, a code query is generated to show details. Use the search panel, it turns out to generate queries. Navigate the dependency graph, more queries are generated under the hood. But here's the problem. Ask an LLM to generate an NDepend code query, and it'll hallucinate fake APIs and made-up concepts. Our solution, MCP tools that transform any natural language question about your code into an actual, working code query or even a code rule. So let's ask Copilot something simple, but not that simple. Generate a code query that detects pairs of methods calling each other, and run it. Here's what happens behind the scenes. First, initialization. Copilot calls the MCP tool Gen Code Query and Rule. A C# link code query is generated, but we don't stop there. Next, Copilot calls Compile Code Query or Rule. Why? To make sure it actually compiles, and if not, to give itself a chance to find a fix based on the compiler error. Only once it compiles cleanly does it move to the final step. It calls Run Code Query or Rule. Now, since this query is about architecture, NDepend generates a graph. And there it is, a single pair of methods calling each other. The current info getter calls the method getInstance, and getInstance, when the provider parameter is null, calls back into getCurrentInfo. That might end in a Stack Overflow. Now look at the generated query. It's surprisingly readable. From just my code methods M1, from all methods M2 it called, create a match if M2 is calling M1. But here's the interesting part. The LLM didn't invent this knowledge out of thin air. It decided to call the tool Gen Code Query and Rule with two specific features: Code Query Essential and Usage Dependency. Usage dependency is exactly what we needed, methods calling each other. If we review the MCP.Server, we see something interesting. There is one source file per feature. Each file declares a carefully crafted and detailed prompt, starting with a concise explanation, then relevant NDepend API details, and finally, sample queries targeting the API. The same goes for the Essential Code Querying feature. It explains the structure of a valid code query. With these two prompts returned to Copilot, the LLM is now an expert in both code querying and usage API. With that guidance, generating the correct query becomes straightforward. Then it verifies compilation, because we explicitly designed the tool to require that step. And finally, it runs the query. Now let's copy that generated query, paste it into the NDepend query editor, et voila! Finally, let's raise the bar. Let's define something truly non-trivial. We ask Copilot, generate a code rule that finds events registered in the constructor of a disposable class, but not unregistered in the dispose or disposing method. Now this is serious static analysis. It identifies 6 distinct features it needs to master before generating the rule. Essential, as usual, for core query structure. Code rule, because we want a rule, not just a query. Interface, to detect iDisposable. Event pattern, to analyze event registration and unregistration. Constructor, to inspect constructor logic. And code element naming, to detect dispose and disposing methods. It's building its expertise step by step. You can literally see it reasoning. And then it generates the C# link rule. And what a rule! Let's run it. First against NodeTime. Result? No matches. The rule passes cleanly. Good sign. Now let's try something bigger, the Paint.NET codebase. 32 disposable classes are flagged. Now look at the generated rule. It's substantial. Here's what it does. First, it builds a lookup of events registered inside constructors. Then it filters only disposable classes and searches for dispose or disposing methods. Then it checks whether those events are properly unregistered. Finally, it generates a clear issue explanation pattern, a detailed description, and concrete fix guidance. Let's zoom into one example, the Canvas class. The collection changed event is registered in the constructor, but never unregistered in the dispose. Let's double-check with ILSpy. And yes, the event is not unregistered. Now, does that automatically mean there's a memory leak? Not necessarily, but it means this class deserves a careful code review, and that's the power here. We're defining sophisticated architectural rules and letting the AI generate them for us. What a journey! You now understand MCP servers, how they work with Copilot and LLMs, and you've seen the NDepend.MCP.Server solving real problems. Ready to build your own? Let's explore the key advice and lessons learned from developing MCP servers with C# and .NET. Let's first focus on MCP Tools design. This is something most people completely underestimate. Too many tools. It sounds powerful. Let's expose everything. Bad idea. Too many tools create decision paralysis for the LLM. Tool selection accuracy drops as the list grows. More tools mean more semantic overlap. Similar names, slightly different parameters, overlapping responsibilities. The LLM starts guessing, and guessing means mistakes. More overlap equals more confusion. Also, keep this in mind. The LLM's context window is finite. Design your tool descriptions to fit completely within it. That's how the model discovers what's available. Here's the key. The sweet spot isn't 50 tools. It's 10 to 20 well-designed, high-level tools. The NDepend.MCP.Server provides 17 focused tools, each tackling a distinct use case. MCP is not about exposing your SDK, it's about exposing capabilities. That's how you make the LLM powerful and predictable. Let's take a look at token consumption when running 4 NDepend.MCP tools in a row to generate, compile, and run a complex code query. Both tool definitions and results consume around 6% of token each. With a context window of 128K, this means around 15K total, which is reasonable for a complex operation involving an entire codebase. Be careful with tool orchestration. Multi-step workflows can work, but they're fragile. Success depends on carefully tuned prompts at every step, and each handoff is a potential failure point. The better approach? Design your tools as self-contained agents with clear, focused purposes. That way, each agent knows its job, and your workflow stays solid. You might say our demos showed tools working in sequence. True, but each tool is independent, with clear responsibility and defined boundaries. The Run Query tool, for example, can execute either a generated query or one you created yourself. MCP tools are procedural and deterministic. LLM intelligence is probabilistic and generative. Combining both is the way to converge toward meaningful answers. Finally, let's mention a common pitfall: mimicking your API with MCP tools. Focus on insights, not API dumps. Don't just list methods or properties. Analyze, summarize, and highlight what really matters. Outcomes, not operations. MCP tools should show what you can achieve, not walk you through every API call. Deliver actionable intelligence, return carefully crafted prompts, suggest fixes, and reveal hidden patterns. Don't leave the agent and LLM guessing. let's focus on MCP Tool Declaration and attributes in C#. As mentioned earlier, we rely on the Model Context Protocol NuGet package. The MCP tool attribute accepts several parameters. First, the tool name. We prefix each tool name with our product name, NDepend. This is a common practice to avoid name collisions when multiple MCP servers are involved. That said, built-in MCP servers usually don't do this, except for Microsoft Learn, so consider this a guideline, not a hard rule. Next, set idempotent to true if calling the tool multiple times with the same arguments has no effect on the environment. Set read-only to true if the tool does not modify the environment. Set destructive to true if the tool performs irreversible changes, and set open world to true if the tool depends on dynamic or unpredictable sources like web searches. Then comes the description attribute. We find it convenient to use C#11 raw string literals, starting with 3 or more double quotes. An MCP tool method itself is declared public, static, and async to avoid blocking threads. In rare cases, Copilot invokes multiple MCP tools concurrently, for example when retrieving different dependencies, but most of the time, tools are invoked sequentially. Copilot may also start multiple instances of your MCP server. However, in the initialize tool prompt, we explicitly instructed to use a single instance initialized once. Each MCP tool receives an injected NDepend service to access the initialized session along with a logger. Both are defined by the main MCP server method. A cancellation token is also supplied by the Model Context Protocol package pipeline, giving the calling agent a way to cancel a tool invocation. All tool implementations follow the same pattern. Log the call and its parameters, retrieve the session, throw an MCP exception if it's not initialized, and then run the core logic inside a task. MCP exception is the correct way to return meaningful errors to the calling agent when something goes wrong.
Now let's cover some tips for writing effective MCP tool prompts. Generate the prompts of your MCP tool with Claude or ChatGPT, but review them carefully. This manual refinement step is crucial and will make or break your MCP server's effectiveness. MCP tools typically bring additional data to the agent, so remember, you understand your tool better than any LLM does. Start with a concise tool description, then add a purpose and use cases section. Include concrete examples whenever possible. If you don't show your agent how to use your tool, it will guess, and it might guess wrong. As mentioned earlier, end your prompts by explaining how to present results. In our context, single-click navigation and indexed lists add significant value. During development, test your tool prompts with standard free models like ChatGPT-4. Remember, you don't control which LLM your users will choose. If standard models work well with your prompts, premium models will likely perform even better. Think of it like testing software on older hardware. If it runs smoothly there, it'll excel on modern systems. Now let's share some practical tips we've learned for designing MCP tool parameters and results. Keep parameters simple. Use primitive types whenever possible. Booleans, integers, and strings. Don't force the LLM to guess complex argument values. We've noticed that for empty strings, LLMs sometimes input null, sometimes an empty string, and sometimes even the literal string null. So we created an isValid method to handle all these cases gracefully. We deliberately avoid reusing records or tuples across multiple tool arguments. This eliminates complexity that could interfere with LLM reasoning. Each argument includes a description to guide the LLM toward the most meaningful value. Some arguments, like the kind of code element on which to gather metric, require a fixed set of values. Instead of defining public C# enums or flagged enumerations, we enumerate possible string values directly in the argument description. Enums get serialized to strings at the protocol boundary anyway, and models work better with semantic strings. Again, we're optimizing for easier reasoning. MCP tools often return collections, like our metrics tool that returns code elements with their metrics. Remember, all results are formatted as JSON for the LLM to read. If your collection is unbounded, it could overflow the LLM's context window. Even if it fits, returning many items when just a few would satisfy the user wastes tokens unnecessarily. When tools can return many items, pagination is essential. The Model Context Protocol package provides a paginated result class, but we had issues making it work properly, so we built our own, and you're welcome to reuse it. Tools with paginated results accept both a cursor and a page size argument. This way, if the user wants more items, the LLM can invoke the tool again to fetch the next page. One final note, since our computations are fast after initialization, we don't need to cache results between page requests. We simply recompute, sort, and slice on demand.
Finally, the best part of MCP tool parameters is their flexibility. If you need to change the parameter list in a future version, it won't break any caller. The LLM adapts automatically. Here are 2 tips to improve your MCP tool responsiveness. First, use progress bars for long-running operations. The MCP protocol includes built-in progress reporting for tools that take time to complete, like our initialize or run analysis tools. Currently, MCP tool progress bars are only supported in VSCode Copilot, not yet in Visual Studio Copilot. The implementation is straightforward. Your MCP tool simply needs to define 3 parameters: the MCP server, request context, and cancellation token. Then call our getReportProgress method, which returns a progress delegate. Finally, invoke this delegate from your code whenever the progress percentage updates. Second, return early and compute asynchronously. Don't wait for all state to be computed before returning from your long-running tool. For example, our initialization tool returns as soon as the analysis snapshot loads. Baseline and issue computations then continue asynchronously in the background. If subsequent MCP tools need this state, they simply await until computation finishes. This works well because Copilot typically takes a few seconds before invoking the next tool anyway, giving your background tasks time to complete. This pattern keeps the agent responsive while still ensuring all necessary data is ready when needed. To wrap up this video, here are a few practical development tips. When you're repeatedly testing MCP tools during development, we recommend using the VSCode Copilot chat window instead of the Visual Studio one. VSCode launches almost instantly, so you can start testing in just a second or two. Visual Studio 2026 has improved its startup time a lot compared to previous versions, but it still can't compete with VS Code's speed. Another advantage, VS Code Copilot Chat includes a progress bar, and you can expand each MCP tool call to inspect the JSON input parameters and the returned result. That level of visibility is helpful while debugging. As of now, the Visual Studio 2026 chat window doesn't offer these features yet, so for fast iteration and better inspection, VS Code is actually the smoother experience. When you need to debug an MCP tool that's still under development, the simplest approach is to temporarily add a debugger launch call in the tool's code. When the agent invokes the tool, the debugger prompt will appear, and you can select a Visual Studio instance to attach and step through the execution. Just don't forget to remove the debugger launch call once you're done debugging. Finally, make sure you log every tool call along with its parameters. Logging is critical, both during development and in production. In our case, the MCP server writes logs to text files in the Artifacts Logs directory, which makes it easy to inspect and troubleshoot behavior later. Logging is configured in a shared Bootstrap base class that's used by both the standard I/O server and the HTTP SSE server. This way, no matter which hosting model you run, you get consistent logging behavior across the board.
Hey, looks like you made it to the end. Thanks for watching. We hope you picked up some useful knowledge along the way. If your product has an API, there are certainly ways to guide LLMs to create more meaningful user value with an MCP server. Check the link in the comments for the NDepend.MCP.Server GitHub repository. It's a great way to level up your Copilot experience. You can build your own MCP tool tailored to your workflow, or use the source code as inspiration for your own implementation.